the second part, so the second lecture is actually completely different from the first one. Okay, so the first one is trying to give you some sense of what is network modeling, because I guess it's quite not too many people working on network modeling in here. The second one I think is more AI. So and also there's no mathematics here, but I think it's a very interesting topic. I just want to share here and try to see your comments on this type of research. Okay, so we're talking about the cybersecurity challenge in the intelligent transportation systems, and basically we are doing two studies in different areas, and I just try to combine it in this whole lecture. Okay, so basically we're talking about the problem, why we're doing this, and then we're talking about two recent papers we're working on. But the two papers is actually more like an introductory level where we didn't do it very in deep. So hopefully this can generate some discussion. Okay, so basically we all know that the AI plays a very essential role recently in the transportation, in smart transport. And first, in 20 years ago, 10 years ago, most of the people working on the transport theory or transportation science, basically, we're talking about some equilibrium, traffic flow theory, and also the discrete choice modeling. Okay, but recently, more and more people, they are trying to use the machine learning, data mining, and AI directly to solve the transportation problems. Okay, so we believe that the machine learning is a tool that can integrate the past data, experience, and demonstrations that can help us to make the decisions directly without using the modeling technique, or it can help assist the modeling technique. Okay, so that's a setting. And also we know that the AI and machine learning has been used in all kinds of different smart transportation applications. So here I try to give you a summary, or from what I can see, these are three major areas that are using the AI and machine learning. The first part is basically making use of the computer vision technique. No matter you are using the, for example, you are extracting the traffic conditions from the CCTV camera or the autonomous vehicle, the perception component in the autonomous vehicle. So basically, you try to make use of computer vision technologies to obtain the data from different sensors. So that's one major area. And the second area, I will call it a spatial temporal data mining and forecasting. So for example, you're inputting the traffic data, or you're forecasting the short-term future, no matter it's the speed, or it's flow, or it's OD, or it's in the road network, it's in the transit network, or in the railway network. So basically, you analyze the spatial temporal data, and then you can, for example, help the personalized mapping service. For example, you can estimate the ETA, or you can predict the flow and passenger flow, or you can predict the OD demand or supply shortage for the Uber, for Uber and Lyft. Okay, so that's the second area, mainly analyze the spatial temporal traffic data. And the third area I would say is mainly related to the control, reinforcement learning. We're talking about the planning and control of the autonomous vehicle. And also it can be the traffic signal control and perimeter control. We can also use the reinforcement learning. Or for the emerging mobility services, we can dispatch the orders, route the vehicles, and you can do that using the reinforcement learning. So that's the three major area that I obtained, that I observed that is closely related to the AI and machine learning. Okay, so there are actually some area in transportation that not very related to the machine learning. For example, the transport planning. Okay, so in transport planning, usually it's still the old-fashioned approach. Okay, but for this area, it's now you see a lot of new model, a lot of papers, especially in the spatial temporal data mining and forecasting. You see tons of paper coming from in this area. Okay, so basically here are some examples. So for example, in the CEV, you use camera to detect the vehicles. So that is computer vision, and also you locate yourself. And also here you can see that even recently we have some end-to-end model to control the connected autonomous vehicle. Okay, so essentially we have the AI and machine learning in the smart transportation system everywhere, and also that is mainly because now we have the data everywhere in the smart transportation system. So you can see this. We actually so different from 10 years ago, we only collect data from loop detectors. We only have very few data sources, but now we have all kinds of data. Okay, so no matter it's from the traditional sensors, or you have V2X communications, you have autonomous vehicles, and you have infrastructures. So basically, in the recent smart transportation system, everything becomes more and more connected, and that means you have more and more data from different sources. Okay, so the issue here is that I think it's 6 years ago or something like that. So they find that in many of the machine learning and AI models, there is a vulnerability issues. So here is a very popular example. So here you can see that we are talking about the object detection, image classification. So basically, you need to tell me whether this is a panda or it's a dog, it's a cat. So here you can see this is an image of panda. And what you can do is that you add some noise, and this noise is very small. So after you adding this noise to this image, you have an almost identical figure. Okay, so this image, to our eyes, is almost the same as this previous image. Okay, but if you put this image to the classification neural network, then the neural network will tell you that this is a gibbon instead of a panda. Okay, so that we call it. Of course, this noise is not random noise. This noise is intentionally designed. So we call this a adversarial sample. Okay, so basically, for each of the image, you can develop some adversarial sample like this, and you can cheat the deep learning method or neural network AI method, so that the AI method can be wrong. Okay, very easily. And actually, to our eyes, it's not difficult. It's not very difficult because it's still a panda. It's very easy to tell. But for machine learning, for machine learning models, it can significantly change its performance. Okay, so we call this adversarial samples, and that actually raises this question: how the machine learning and AI is vulnerable, or how we can trust it in our application? Because in the future, we will use it every day. For example, we even ask the the AI model to control our vehicle. But if there's something like this happens, then that would be dangerous. Okay, so basically, this raises our concern in the vulnerability and the robustness issue. Okay, so here we are saying that we are now using AI and machine learning in the transportation management, in smart transportation every day, but we notice that it becomes a double-bladed sword. So it brings efficiency, it brings benefit, but it might give you some issue, and you have to understand how it can make troubles. Okay, so that's the idea. So this is some research from the AI community. It's actually from the CV community. So this is an example. So you can see that this is a stop sign. And what they do is that they did some patch on this stop sign. Okay, so this black and white patch. Okay, so after they make this patch, and the autonomous vehicle no longer identifies this as a stop sign. It becomes a speed limit. Okay, so that means the vehicle won't stop at this sign. And this patch is actually, for our human eyes, is still a stop sign. But this patch is actually intentionally designed that to cheat the machine learning algorithm. Okay, and similarly, this is another example. So this is a lane detection algorithm. So basically, the lane detection tries to detect the lane mark. So basically, it gives you the drivable area for the autonomous vehicle. But because the road has some random marks on the road, and sometimes this random marks becomes this patch. It basically it has some similar function like this patch, and then you can see that the lane detection becomes much more worse. Okay, so this also creates a lot of safety issues in the autonomous vehicle driving. Okay, so in the autonomous vehicle, there are actually several papers on this adversarial attacks, or we call it vulnerability issues. But if you're talking about some machine learning applications in transportation, we haven't seen too much studies. So that's what we want to do. Okay, so basically we want to do some studies related to the smart mobility applications. Okay, so some background knowledge about the attack on the AI models. So in general, first thing, there are multiple categories of the attack. Okay, there are actually a lot. So here I just give you three most dominating one, the top three, which we call it evasion attack, poisoning, and inference attack. Okay, so it's different. So let's talk about the one that is the most easy to understand, poisoning. What does poisoning means? It's basically you try to hack the training data, because your AI model is definitely trained from some data, right? If you can hack the training data, for example, you insert some data samples that is toxic, and then basically you poison the training data, and then your AI model may be perform weirdly in some circumstances. Okay, so that is poisoning attack. Okay, so poisoning attack, if you are interested in this part, I highly suggest you check Professor Jeff Beck from University of Washington. Okay, so they are working on quite a few papers related to the poisoning attack. Okay, so here basically you are perturbing the data set. Okay, so another one commonly used is called the evasion attack. So the Panda example is the evasion attack. So the evasion attack does not talk about the training data. It's basically modifying the input of the learning model. It only happens in the inference stage. Okay, so for example, you have your original image like this, and I try to add something, then this is evasion attack. So these are all evasion attack. So you don't touch the training model. You only touch the input data. Okay, so these two are the two major ones. And the third one is called inference attack. The inference attack is actually not an attack. It's more like try to expose the training model. For example, you can, from the output, you infer the weight of the machine learning model. Okay, this is called inference attack. For example, if you can guess what is the structure of ChatGPT and what is the weight in the ChatGPT, this is inference attack. Okay, so those are three common ones, and there are actually more. So for example, this is extraction attack. I won't mention here. And for this talk, we are mainly talking about evasion attack. Okay, so we're perturbing the input. And also for the attack, there are multiple goals. Either it can be targeted, so you have some special purpose, or you don't have purpose, you just want to destroy the whole system. Okay, and this one is important. We call it knowledge restriction. So basically, when you initiate this attack, what type of information that you have? Okay, so usually there are three categories: white box, black box, and gray box. White box means that you know the structure of the neural network, or you know the neural network. Okay, so which is actually not very realistic, but this gives you more property. So black box means that you completely don't know what happens here. Okay, so for example, if you want to attack ChatGPT, then it's a black box attack because you don't know the structure, you don't know the weight of ChatGPT. Okay, and gray attack, gray box is actually in the middle. So that means you know something, but you don't fully know the network, the model. For example, you only know the neural network structure, but you don't know the weight, or you basically know something. We call it a gray box attack. Okay, so basically for this talk, we are talking about evasion, targeted, and black box. Okay. So in general, when we talk about the attack, the key issue is not attacking the system. The key issue is how do we defend? How do we make our system more robust and more reliable? Okay. So this is actually an open question. So in general, we call it a cybersecurity challenge in the smart transportation system. And this is actually a interdisciplinary research field. So you can say that it relates to the hardware, it relates to the transportation, it relates to the AI and the cybersecurity. Okay, so 3 years ago, UC Berkeley, they published a white book. I think it's a white paper. So they're talking about the cybersecurity risk about the smart city technologies. I think this, so in recent years, this becomes an interesting topic that we want to study. Okay, so there are actually a lot of questions in this area because this is a pretty new area. So the first thing is how severe it is, what is the impact, and also how do we identify the attack, and how do we mitigate the attack, and how do we prevent the attack. So there are a lot of things that we can answer. We can research. So for now, what we are doing is that we just do a very preliminary study. We just develop some attack and try to see how important it is, whether it's a severe issue. Okay, so that's the idea. And then we're talking about two papers. This paper is we are developing an attack on the traffic prediction model. Okay, so basically a spatial temporal deep learning based traffic prediction. What happens if we change the input? How does that make your prediction becomes worse? Okay, so the motivation is actually from a very interesting experiment by an artist. This is a German artist. Maybe you'll see the news from different places. So what they are doing that this German artist, he has basically opened up 99 cell phones and then use all those cell phones to open up this Google Map. Okay, and then he just take all those phones and walk slowly on this road. Okay, I'm not sure if you know how the Google Map calculates the travel time. Basically, you are using your cell phone, and then you send out your GPS location back to Google, and then Google calculates the travel time based on your trajectory. And if you have a lot of people using Google Map, then the travel time becomes very accurate. Okay, so this is from the theory is from UC Berkeley, Alexandre Bayen. He did a lot on this. Okay, so this is a fundamental idea. But what he did is basically he intentionally opened up all those Google Maps and just walk slowly. And because he walks slowly, so the travel time based on all those cell phones becomes very slow. Okay, become very low. And then in the Google Map, on the real time, you'll find that Google Map identify this becomes a congestion. Okay, so that's actually an attack initiated by one person. It's very simple. And actually, very interestingly, this is a street in front of Google Berlin. Okay, so this is a headquarters in Google Berlin. So it's actually, this is done by an artist, not a transportation engineer. And I also read the news. So there are several people in mainland China. They did exactly the same experiment. So all the maps behave similarly to the Google Map. So basically, that means most of the mapping services, they cannot resist on this kind of simple attack. So this is actually a simple attack. You modify the input of the network. Okay. So this is a idea. So this is a motivating idea. Then we say that if we make use of this attack, there are actually a lot of parties that they are interested in doing this. For example, if you want to, you can actually, if your mobile phone is controlled by some app, then you can send out this kind of wrong information to the system. Or you can imagine if Uber want to do this kind of attack, because Uber already have a lot of vehicles, and then they can clue together and to try to send this wrong signal to the system. Okay, so essentially, different parties they may take advantage of this AI model, and that can create some benefit, or they can take advantage from it. Okay, so actually, this is also from the news in China. So this is in Shanghai. What they did, those are actually the Uber drivers in mainland. What they did is that they just opened up a lot of apps and to create a congestion in this area so that no drivers will come. Okay, so they can take orders much more easily. Okay, so this is 2 years ago in Shanghai. This is a news I just found from a TikTok. Okay, so you can see that you can see that they open up a lot of cell phones. Okay, so to create a congestion, because there's a congestion, then other drivers, Uber drivers won't come, and then they can get this order easily. Okay, so there's a lot of motivation that initiates our study. So basically, we just want to evaluate if we can do this similar attack. For example, we can modify the travel time for each specific link. How does that affect the whole system if we are using some deep learning method to do the prediction? Okay. Then we develop a attack, we call it a diffusion attack. That means we want to choose a limited set of nodes on the network so that we want to degrade the overall performance of the neural network. So basically, so this is the original network, and you have the travel time on each of the link. Okay, so say for example, we pick, if I ask you only pick one node, which node you should pick to make the make your effect of the attack the highest? Okay, so that's a question. And here I'm not saying one, I'm saying 2 or 3. I just give you a number, and then you need to pick those nodes from this network. Okay, we call it a diffusion attack. Okay, so this is a setting. So in general, we are assuming a graph convolution neural network based traffic prediction model, and then you have node as the traffic state as each road, and basically you have the historical data of the traffic state. Okay, and then basically based on the historical traffic state, you can predict the future y. Okay, so what we want to do is that we want to add a perturbation u to the input. Okay, so x becomes x prime. So basically you are adding a perturbation. So this perturbation is similar to the attack by the German artist. You just modify the travel time for each for some of the link. Okay, and then you can create this inference. You can largely you can change the performance of the neural network. Okay, what we want to look at is how do we choose this u such that the performance change is the highest for the neural network. Okay, so this is a setting, and this problem you can formulate it as a integer programming problem. Okay, so here you can see that we want to maximize the effect. Okay, such that first thing, the u cannot be too much. Okay, so it has to be very small, because you can if it's small, then in the evasion attack you have to make it small to not be detected. Okay, and also zi is a node that we want to attack. Okay, so here each zi has a budget. If you want to attack some busy road, then maybe you have higher cost, and in total you have a total budget. So given this limited budget, so which node you should attack? So that's a question. Okay, so here zi is whether we want to attack or not, and the u is how much we want to attack. We want to increase the speed, or we want to decrease the speed on this road. Okay, so this is a integer programming problem, so it's difficult to solve. And then we actually decompose this to 2 sub-problems. The first problem, we say that we are given a fixed set. So suppose that we know which node to attack, and then how do we do the attack? So how do we optimally determine the perturbation? Okay. The second one is how do we select the node? Okay. So basically, we just try to change the 2 decisions into decompose this 2 decisions into 2 sub-problems. Okay, so choosing the node and also determining the perturbation. Okay, so the first problem is actually a black box optimization. The first problem is you're given the set of node, you just try to determine the perturbation. Okay, the second one is choosing the node. We reformulate it as a next step problem. It's an integer programming problem. So let me give you more details on this. Okay, so in the first problem, what we want to do here, you can see that we already know which node to attack. What we want to do is just determine this perturbation u. Okay, so because the attack on the deep learning is black box, because deep learning is black box, then this becomes a black box optimization, because here phi is a deep learning. Okay, then what we can do is that we just solve it using some black box optimization problem. So here we are using a very popular one that can be used to solve the high dimensional problem, which is called SPSA, simultaneous perturbation stochastic approximation. The idea is very easy. So you have some initialization u, and you add a perturbation, you minus a perturbation, you have u plus and u minus. And then you just evaluate the u plus and u minus and divide it by the perturbation. So this gives you a approximation of the gradient. And then you use this gradient to update the u. You just keep doing this. So we call it a simultaneous perturbation because you can see that you perturb this high dimensional u at the same time. Okay, so this is a popular algorithm to solve the high dimensional black box optimization problem. Okay, so it turns out that this solution algorithm is efficient on this problem, and it gives you a good conversion or convergence rate on high dimensional problems. Okay, so for example, the one that maybe you are familiar with, for example, the genetic algorithm, all those, it cannot solve the high dimension problem. Okay, so this one particularly is for high dimensional problem. Another one very useful for high dimension problem is called DE, diffusion evolution, if I remember correctly. That one we compare with SPSA. The performance, this one is better, so that's why we use this one. Okay. So the second problem is that we know the attack effect. We know the U. We just want to determine the which node to attack. So this question is actually very similar to the knapsack problem. The knapsack problem is basically you have different items with different weight and different value, and you have a total bag that has a weight limit. You just try to put all those items into this bag such that your total value in the bag is highest. Okay, so very fundamental problem in the integer programming. So here the resource, the budget is our, the budget to attack is actually the resource in the knapsack problem. And the decision is which node to put in the bag. Okay, so basically which node to choose. And then we have the weight of the item is basically the cost of the attack. And the value of the atom is basically the attack effects. Okay, so the only thing different is that in this problem, we don't know the attack effect actually. So what we did is that we are using the approximated effect from the SP1. Okay, so basically we are iteratively solving this two problems. We solve the SP1, we estimate the attack effect for each node, and then we solve SP2, and then we go back to solve SP1 again. We just keep doing this. Okay, so then the greedy algorithm, the knapsack problem is easy to solve. You just use the greedy algorithm. And the greedy algorithm is also very straightforward. You always choose the item with highest value over weight. So the value over weight actually evaluates the cost effectiveness. Okay, so you always choose this one, then you will get a roughly good result. Okay, but this the knapsack problem is integer programming, so it's NP hard. At least NP complete, but so you cannot. If it's a large scale problem, it's difficult to find the optimal solution. But the greedy algorithm usually give you a reasonably good result. Okay, so if you have this two, then so we solve the problem. What the next thing we did is that we just try to do experiment in different cities, and we try to evaluate different prediction models. So here we are working on 4 different cities: LA, Hong Kong, San Francisco, and Seattle. And then we also test on 3 different prediction models: TGCN, STGCN, and A3T-GCN. So TGCN is very popular, I think. It's very, very baseline. Okay, and also for our approach, we are using the knapsack to pick out the node. There are other approaches to pick the node. For example, you can just choose the largest page rank as a node to attack. Or you can use between it some complex graph theory. You can also use these indicators to pick the node. Okay? So the first thing we look at is that if we only attack one single node, and we look at how it change the performance on the neighborhood. Okay, so we are looking at if we perturb this node, what's the change of the prediction for this node? What's the change of the prediction for the second for the one hop? What's the change of prediction for the 2 hop? So you have this figure. So you can see that you change this node, the prediction of this node definitely change a lot. Okay, and also its neighborhood also change. The one hop neighborhood also change significantly. But if you look at the 2-hop or 3-hop, it already become marginal. So after the 3-hop, the change actually is almost 0. That means if you perturb one node, then the effect actually only diffuse to the 2-hop at most. So that's why we call our attack a diffusion attack. Basically, you just try to pick some node and diffuse to the neighborhood. Okay, so that's an experiment on one single node. And here you can see that we try to test on different algorithm and so 4 different cities: Bay, Seattle, LA, and Hong Kong, and 3 different traffic prediction model: STGSyn, TGSyn, and A3TGSyn. And also we also view this as a semi-black box or black box algorithm, and we look at how much is perturbed. So you can see that here we also test on DE. So in general, what we propose, the solution method gives you the highest attack effect. Okay, so this unit is AAI, so it's average of attack influence. The unit is km per hour, so that you can just think of it as the maximum we can change. So previously the prediction is 40 km per hour. After the attack, the prediction can be 20 or 60. Okay, so basically we can change at most 20 km per hour of the prediction. Okay, so which is actually not very high, which means that the traffic prediction model is quite robust in this sense. Okay, and here is some, so the triangle gives you the node that we pick, which node we should attack. You can see roughly it's distributed on this network, okay, because it's diffusion attack, because it only affects the 2-hop neighborhood. So in general, we want to distribute all the node to attack in this whole network. Okay. And we also try to look at some defending strategies. So there are 3 popular approach to increase the robustness of the neural network in the graph neural network, which is called drop out, drop node, and drop edge. Drop out is basically dropping the feature. You just intentionally set it 0 every time. And drop node is you just randomly drop the node when you train the model. And drop edge is you drop some of the edge in the training. Okay, so in general, we find that drop out works the best, and drop node and drop edge sometimes can make the model worse. Okay, so that's the first study we did on the traffic prediction model. The second one, we try to look at the reinforcement learning. Then we are developing some attacking mechanism on the reinforcement learning. So in particular, we're talking about the traffic signal control. Okay, so the setting is very straightforward. We all know that there's a lot of research on the traffic signal control using the reinforcement learning. For example, in mainland, there are some city brain plan, and in US, especially in University of Michigan, they have some smart intersection project that they want to build the intersection with a smart traffic signal control. Okay, so this can usually it can be done by reinforcement learning on some smart agents. What they are doing like this. So they look at they use an agent to control this traffic signal. Okay, so the state may be the traffic state or queue for this intersection, and then what they can do is to switch the signal from green to red or from red to green, and then they evaluate the model, they train the model. So this is reinforcement learning in traffic signal control. You'll see a lot of paper every year, blah blah light. You'll see a lot of paper like this. Okay. So what we want to do is that we want to train an attack. We want to have a model to attack this reinforcement learning model. And here the setting is that this traffic signal trust the state. They believe that the state is correct. But this state is actually from the connected vehicle. The connected vehicle sending the information to the traffic signal. And if we can manipulate this information, that can actually deceive the traffic signal. Okay, so that's an idea. And I think 2 years ago, there's an attack in Russia after the war. There are some people, they attacked the largest ride-hailing company in in Russia, which is called Yandex. What they are doing is that they hack into their company, and then they ask all the empty vehicle to go to the same location. Okay, so you can see that all those vehicles go to the same streets, and then it creates a huge congestion, and basically there's a gridlock for over 3 hours. Okay, so that means it's possible that you can send some falsified information to the system, and that can manipulate the system. Okay, so then here is our setting. Our setting is we say that we believe that the traffic signal control is controlled by some smart agent, and it's a black box. We know nothing about it, but we know that it's receiving the information by the roadside unit, and the roadside units control the traffic signal. Okay, then we assume that we have a group of colluding vehicles. So those vehicles, they are working together, for example, the Uber. And then they can send some wrong information, falsified information to the roadside unit. Okay, so here the easy one is that, for example, it's just one vehicle, but it can send out the information about 3 vehicles. For example, there's only 1 vehicle waiting here, but you just send out there are 3 vehicles here. And that can actually force the traffic signal gives more green light to this direction, because you are falsifying more vehicle on the road. Okay, so basically we want those colluding vehicles to collaborate together and to reduce the total travel time for themselves, for this group. Okay, so again, we are developing another reinforcement learning method. Okay, so basically we are using a reinforcement learning to attack another reinforcement learning. Okay, so for this reinforcement learning model, we also look at the traffic condition, and then the action is how do we send this falsified information. Okay, so we can send, for example, the reality is we have 1 vehicle. We can send out there are 2 vehicles, or we can send out there are 10 vehicles. Okay, and the reward is that we want to reduce the total travel time for these colluding vehicles. Okay, so this is basically a competition and a collaboration game. So basically you have competition because each of the vehicles, they are working separately, and collaboration is that they can sending signal to minimize the total travel time for this group. Okay, so this is the idea. Okay, so basically we develop a framework, a multi-agent reinforcement learning framework, and basically we just try to use different components to incorporate the state. For example, we include the time, location, vehicle, status, and including vehicle, all those as states, and we just use MLP to get some encoding here, and then we combine all those encoding, we get a vehicle interpreter, and also we allow the communication between different vehicles. Okay, so basically we combine all of them, and then we are using a PPO structure. So we are outputting the actor and critic. So the PPO is a very commonly used approach in the multi-agent reinforcement learning. So basically it's an actor and critic learning scheme. So we are using the MLP plus, MLP is used for the encoding, and graph attention network is used for communication. Okay, and basically we are doing the parameter sharing. Basically the only difference for the critic and actor network is the last layer. Okay, so all the previous layer is parameter sharing. We're using the same structure, same parameter. Okay, so the only part is actor outputs the action and critic outputs the value. Okay, so a very standard PPO structure. Okay, so basically we want to, given the smart traffic signal as a black box, we want to train this model to attack the smart traffic signal. Okay, so we are testing on a micro simulation software, Sumo, and this is Monaco City. Okay, so this is a network, and the traffic signal model, we are using a previous paper. Okay, we will directly use their trained model as a traffic signal, and basically we are training another reinforcement learning to attack on this. Okay, so in general, you can see that this is a convergence curve. After 1,000 episodes, you have a good attacker result, and also we demonstrate that all the components in our model is useful. Here, from an engineering perspective, so each of the episode is actually, in reality, is 1 day, right? So 1 day you learn the traffic signal a little bit, and in the second day you learn a little bit. So here you can see that, in general, after 500 days, you already have a very good result. Means that you have to keep testing the system for 1 year, looking at the system's response and action. Then you gradually understand how the traffic signal reacts, and then your model becomes useful. Okay, so here, after 1 year's learning, your vehicle could basically take advantage of the traffic control system. Okay, so that's one finding. And I think this also because the multi-agent reinforcement learning is difficult to train. Okay, but that's the best one way we can have right now. And also we compare some baseline. For example, all one means that all the vehicles just report that it's just one vehicle. So it means that there's no attack. Everyone tells the truth. And all 10 or all 5 means that they're always lying that they have a lot of vehicles. Okay, so here you can see that all 5, so we look at the total travel time of the including vehicles. So you can see all 1 is the base case. And if you treat them as all 5, all 10, you can see that the total travel time is already reduced. It's basic because if you treat that there are more vehicles on this road, then the traffic signal gives you more green time. Okay, but this number is actually a little bit lower than this one. That means there's still some collaboration here. That because we have a group of vehicles. If 2 vehicles at the same intersection, maybe 1 vehicle should lie, another one should tell the truth. Okay, so that's the idea. So you can see that there's still a collaboration and computation problem. And another very interesting problem is here. You can see that if you get a lower total travel time, you are taking advantage of other vehicles that's not in the group. So here, a significant increase. So the average travel time for other vehicles increase. Okay, so you are taking advantage of other vehicles. And another very interesting experiment we have is that we're looking at the number of including vehicles, the size of the fleet. So in general, if you have more vehicles, then the total travel time saved is definitely increasing. That's for sure. But if you look at the average travel time improvement, it's actually decreasing. That means if you have more vehicles, then the attack effect is becoming marginal. Okay, so also very easy to understand. Okay, so that's the second study we did. So you can see that these 2 studies just give you an idea how robust our system is, and we can develop some method to attack the system. And so here are some implications and discussions. So we are seeing that you can see that there's still some issue in the vulnerability issue in the system. So for different parties, you should do something, right? For example, the public agencies, you should make sure that your system are aware that there might be a cyber attack. You should be defending on that. And for private sectors, for example, Uber, and they should have this principle that they should not benefit their own interests by sacrificing others. For example, the including vehicle attack, it can be implemented very easily by Uber. But this should be forbidden. And also for travelers, you can see that some of your information, like their trajectory, can actually be used to attack the system, so which you have to protect. Okay, so in terms of some defending strategies, here we just have some summarization. So first thing, the very easy strategy is that you just do some data verification. So when you receive those information, if you have some certification mechanism or verification mechanism, then you completely avoid all those attacks. Okay, but maybe it becomes difficult. And then the second one, we find that if you use a very complicated deep learning model, then it becomes more vulnerable. Okay, but if you are using simple MLP or those models, then it's very difficult to attack. The attack effects is very low. So then there will be a trade-off between the complexity and the robustness of the deep learning model. And the third one is that you can see that from all these 2 papers also all suggest that your attack algorithm has to learn for some time before it can take effect. So if you can frequently update your AI model, that can definitely help to prevent this attack. And also, we also find that if it's a black box attack, the effect is actually much weaker than the gray box attacks. So that means all those public agencies, if you're making your model in use, you should strictly hide your model structure and your parameters. So that can be very useful. And last one is some active defending strategies. Basically, you can use some anomaly detection to detect all those normal signals to filter it so that it won't be attacked. So that's just some suggestion and some future studies. And actually, I think some professors in Abu Dhabi, back in South, I forgot in NYU Abu Dhabi, they are working on this, and also there are professors in UW, they are also working on this. Okay, so that's the second talk, which is more related to the AI part. Okay, thank you.
Any questions from the floor?
I'm also really interested in the topic of cybersecurity. So thank you for your great presentation. I want to ask, when you want to come up with a cybersecurity research topic, it is more suggested to think from question-driven or data or model-driven. For example, question-driven make some scenario happen in the real life and then think about how to test it in your cybersecurity. Data-driven or model-driven is just change the quantity of data or to test the model. Yeah, which is suggested.
Yeah, thank you for your question. So there are actually a large community, group of people in computer science that are working on this universal tag. But in transportation, I think the key issue is that you need to find out a question that is feasible and also it's worth studying. For example, when we talk about evasion attack or poison attack, you have to come up with a setting that is reasonable. Everyone can buy your story. So that's why I try to give you some real-world example. So this actually happens, so we should do something. Okay, so I guess that's my strategy. I just try to make use some real-world example to associate the existing theory. But how do we find a new question? I'm not sure. But yeah, if you can find a new setting that is everyone think is worth studying, then I think you should do it. But I think a lot of effort should be in how to find a good question or problem setting. Okay, thank you.
Other questions?
Yeah, for this. Okay. Hello. So this is not regarding the cybersecurity part. This is more on the statement earlier that you said. In transport planning, all methods are still used compared to the AI and all the machine learning. What are some impediments, or why do you think transport planners are still not going to the more?
Oh, I see. Okay, so maybe this is a controversial statement. But in general, I would say if we talk about penetration rates, then the transport planning, this area is actually less penetrated by the AI. I think the key issue is the data. We don't have too much data in that, because the transport planning, we are talking about 5 years later, 10 years later, and then you collect data every 1 year or 5 years. So you don't have that much data that can be used to train an AI model. I guess that's the most important difficulty or challenge in the
very new.
I would say there are actually several recently there are pretty a lot of paper using AI to do the urban planning and also city design. But I think it's still very preliminary. The issue is the data and also how do you verify? That's also a problem. So in most of the machine learning problem, you have the training, validation, testing, you have a very close loop to evaluate your model. But planning is not close loop. You're planning for 10 years and you can evaluate after 10 years. It's difficult, actually.
but we will come to a point that we will utilize them.
Right.
We will come to a point later on that we will utilize
Well,
them.
I'm not sure.
Okay.
Maybe. Part of.
Maybe.
Part of.
Thank you.
Thank you.
Other questions? Please.
Thank you for your presentation, and I just want to check if I understand your presentation right. In your presentation, the attack means that individual vehicles send fake information to the system and take advantage from the fake information. It means
So the vehicle send the wrong information to the system. Yes.
yes, and take some advantage from it.
Yes.
Reduce the vehicle delay.
Yes. Reduce their delay. So it's not total system delay. It's the delay of those vehicles.
Then every vehicle in the system send the fake information, and every vehicle try to reduce their vehicle delay.
Okay, so we have basically for all the vehicles in the network, we have two groups. One group is we call it colluding vehicle, means that they collude together and they want to try to reduce their travel time. The travel time within the group, and there's other vehicles that are just perform normally. So basically, those colluding vehicles, they send the wrong information and they want to reduce their travel time. This colluding vehicle can be 1 vehicle or can be 10 vehicles. We can modify this number and we can look at the effect.
Do we have other questions?
Yeah, maybe a silly question. Your ML signal model, you trained for many years, and could be now I think it's very robust. Then, what if really a lot of cars are going to the signal? It's not just attack, but in reality somehow there's some events. So suddenly a lot of all of a sudden a lot of cars are going to that system, which is a intersection. Then how your system or your signal can identify if this is fake or it's real traffic.
That's the issue. Actually, in our paper, we don't do any defending. Okay, so we are doing attack. So suppose there's a lot of vehicle already, you can make it even worse, and then you have more green time. And then, for example, the first you have to wait for 2 rounds, and now you only need to wait for 1 round. You still take advantage. So basically, exaggerating the congestion definitely gives you some benefit for those vehicles. But how do we detect? That's the issue. I think it's very difficult to. We are talking about anomaly detection, and it's very difficult to detect whether it's an attack or it's a non-recurrent traffic condition because it's very similar.
Yeah.
If we do this attack very carefully, then maybe it's almost like a non-recurrent traffic condition. So, so what we propose is still, I think, data verification is much easier. But that's not our field because we are transportation engineering. I think some communication person should do something here to prevent this.
Okay, thank you. I think this slide is very useful for me because there are so many algorithms in terms of machine learning, deep learning, and reinforcement learning, and more algorithms will be in development, right? So it seems the classification by deep learning and reinforcement learning is based on your experience, and I think you categorized that deep learning is suitable for that map service or something like that. Then what is the criteria to classify the use cases by deep learning and reinforcement learning? So this is good for that, and that is good for that. So what is criteria based on your experience?
How do we evaluate whether this model is good or not?
No, it's like a kind of classification criteria. You think the traffic management for traffic flow, metro passenger flow. You think deep learning is suitable for that analysis, and the reinforcement learning is good for route planning and control.
I see. Yeah. So
I
I guess this classification is not very precise because reinforcement learning also includes some deep learning. So here maybe I would say it's more like computer vision, spatial temporal data analytics and control. Right? So the task is actually specific, very straightforward. You have 3 tasks. So here I'm talking about reinforcement learning is more like control. I think you're right. So I shouldn't say deep learning. I should say spatial temporal data modeling.
Okay.
The second part.
So reinforcement learning is for more better part, like controlling AVs and controlling
Controlling
traffic
everything.
signals.
Control everything is the third part. And second part is more like estimation, prediction, imputation.
Okay. So,
And first part is more like collecting data. So that's the 3 major areas I find useful of AI.
Okay.
So if there's no more question, let's give Professor Ma a big hand.
Thank you.